Start. The next speaker in the afternoon session is Sahil Joshi from the Indian Institute of Technology from Ropar, India. Please, you can start.
Okay. Good evening, everyone. I would like to thank the organizers for this opportunity to share my research work in this conference. So in this talk, I will be talking about some not determinant formulas. So let us begin. So this is based on a joint work with Komal Neki and my supervisor Madheti Prabhakar. I want to hide this thing. Oh yeah, it's gone. Okay, so as we all know, a link, n-component link is a subset of R3, which is the image of a homeomorphism of finitely many disjoint copies of the unit circle into R3. And a knot is simply a one-component link. So two links are said to be ambient isotopic if there exists an isotopic deformation of the ambient space R3 such that H naught is the identity and H1 of the first link L1 is actually L2. So in this case, we say that these two links L1 and L2 are ambient isotopic. So the central problem in knot theory is to classify knots and links up to ambient isotopy. For instance, if we see this link, just a moment, this. So if we see this link, it looks like it is knotted, but actually this link is ambient isotopic to the trivial link. One can continuously deform this link and it will turn into the trivial link. So if so these questions like we want to distinguish between pair of links and we want to classify them up to ambient isotopy. So if we want to say that two links are not ambient isotopic, then we have to look for invariants of the ambient isotopy. So one such invariant is the determinant. So it has a simple definition. If V is a Seifert matrix for the link L, then the determinant of this link is defined as the absolute value of the determinant of V plus V transpose. And it has many other equivalent definitions. Like alternatively, determinant of a link can be defined as the order of the first homology of the double cyclic cover of S3, which is branched over the link L. Similarly, it is the absolute value. It can be defined as the absolute value of the Alexander polynomial evaluated at -1. So if G is the Courbet's matrix, it's the absolute value of its determinant is also the determinant of the link. And it can also be evaluated from the Jones polynomial by substituting t equal to -1 and take the absolute value. And if M is a coloring matrix for this link, then we consider any first minor of this matrix M, its determinant, and the absolute value of that quantity is actually the determinant of the link. So these are some general formulas for the determinant. In particular, if we have an alternating link, then there are other combinatorial formulas for this determinant. So the determinant of an alternating link can be defined as the number of spanning trees in the Tate graph GD, which comes from an alternating diagram D of the link L. Similarly, by Krebs approach, it is also equal to the number of monocyclic states in the projection D hat. If we look the D hat as an immersed curve in R2, and the number of monocyclic states is actually the determinant. So to obtain a monocyclic state, we have to consider splicing at a crossing. So the number of ways to splice a crossing such that we get a monocyclic state is actually the cardinality of that set is the determinant. So a generalization of this result is due to Champanecker and Kaufman that if D is any link diagram, so it works for non-alternating links also, and GD be its Tate graph, and T is a spanning tree in GD, then if we look at, and VT is the number of positive edges in D. So if we look at this set, the set of all spanning trees in GD such that the number of positive edges in T is equal to K and denote its cardinality by Sk, then determinant is given by this alternating sum of number of spanning trees. So these are some general formulas. So the determinant can also be computed in this way. So Burrow representation is actually a very important tool in knot theory. So if Bn is the Artin's, denotes the Artin's n braid group, and GLn minus 1 is the group of matrices of order n minus 1 with entries from the Laurent ring in the variable T with coefficients from Z. Then the reduced Burrow representation is defined by these equations. So if beta is any braid and beta hat is the closure of that braid, then its Alexander polynomial is related by its Burrow matrix, the Burrow matrix of the beta, by this relation. So here we can see that the Alexander polynomial is determined up to a certain factor. So if we substitute T equal to -1 in the left side and evaluate this Burrow matrix minus identity, this determinant at T equal to -1, then for some cases, like if n is odd, one can evaluate the Alexander polynomial at -1 and so will get the determinant. So we will use this formula of Burrow later to obtain determinant formulas for some families of knots and links. So let us look at some families which are objects of our interests. So torus link with parameters P and Q, which is called the torus link of type P, Q, may be defined by the closure of this braid, which is the toric braid, sigma 1, sigma 2, sigma up to P minus 1 raised to power Q. So this is the generating braid and Q is the repetition index. So this is a very well-known result that this T of P, Q is actually equal to T of Q, P. So which is given by this, the closure of this braid. Similarly, weaving knot is another closely related family of knots and links, which is related to this torus links. So with two parameters P and N, positive integers. So it is the closure of this braid where we change the sign alternatively. So it is sigma 1, sigma 2 inverse and so on. So if we look at weaving knots of 3 strands, so it will be just sigma 1, sigma 2 inverse raised to power n. So a generalization of this class is the class of hybrid weaving knots. So where we are allowed to take sigma 1 to the power m, where m is any positive integer. So this family is recently studied by Mishra and Ramadevi and Vivek Singh. And there is another closed generalization of this family, which is the family of twisted generalized hybrid weaving knots, which is denoted by Q hat. And it is defined by 4 parameters, m1, m2, n. These are the positive integers and L is any integer. So it is the closure of this braid word, which is sigma 1 power m1, sigma 2 power minus m2, whole raised to power n. And there is a twist, which is sigma 1, sigma 2 raised to power 3L, which is a full right twist if L is positive and equal to 1. But we are allowed to take L to be any integer. So these are the families of our interest. One last family is the family of spiral knots, which is a generalization of torus links as well as weaving knots. So it is defined by 3 parameters, n, k, and n minus 1 tuple epsilon. So it is the closure of this braid. Now we are allowed to take sigma 1 raised to epsilon 1, where epsilon 1 can take value either +1 or -1. So if all epsilon i's are equal to 1, then we get the torus links. And if epsilon 1, epsilon 3, 5, so are +1, and the epsilon 2, epsilon 4 are equal to -1, then we get the weaving knot. So the problem of our interest is the general formula, to derive general formula for the determinants of these families. So for torus links, we want to know a general formula for the determinant. So for torus knots, already Breland, Oesper, and Talman in 2009 answered this question that if P and Q are both odd, then the determinant is 1. And if P is odd and Q is even, then the determinant is P. And the case when Q is odd and P is even, in that case, the determinant will be Q. But we do not know a general expression for the determinant when P and Q are both even. So for the case of knots, that is when GCD of P and Q is 1, we know the determinant formula by these authors. Similarly, for weaving knots, we do not know a general formula for the determinant, but for P equal to 3, OSPER in 2005 first answered this question. For P equal to 4, Kim, Stees, and Thalmann answered the problem of calculating determinant of weaving knots in 2016. And for N equal to 2, it was established by Dowdall in 2000 et al. And in 2010. Similarly, we are interested in knowing a formula for the twisted generalized hybrid weaving knots and spiral knots. So for spiral knots with up to 4 strands in the same paper, Kim, Stees, and Thalmann have already answered. So let us look at these results. So if phi is the golden ratio, 1 plus root 5 by 2, Fi is the ith Fibonacci number, Cj is an alternating sum of first j Fibonacci numbers given by this expression, and Lk is the kth Lucas number. Then the determinant of the weaving knot on 3 strands can be given by this expression in terms of the golden ratio. So this was the formula in the second equation, which was derived by OSPER in terms of Cn, where Ci's are basically summation of Fibonacci numbers. So in 2005, this expression was obtained. Later, Stoimenau showed that this determinant can be given by this expression also, where Fn is the nth Fibonacci number. So it is given by F2n plus 2 times summation of F2i, where I goes from 1 to n minus 1. So this was in this paper, and Kim, Stees, and Thalmann in 2016 make a reduction of this formula and showed that this is actually equal to 2nth Lucas number minus 2. And recently, Burton also used a method to find this determinant and gave that it is actually equal to this expression. So let us look at the proof of this one. So the determinant values are actually a well-known sequence of integers. So in the online encyclopedia of integer sequences, these determinants are denoted by this sequence A004146. So these are the values of the determinants 1, 5, 16, 45, and so on. So these are precisely Lucas number 2n minus 2. So our method to prove this result was based on a result of Mishra and Staffeldt. So by studying Hecke algebra representations of the braid group, 3-braid group into the Hecke algebra of type T, 3, Mishra and Staffeldt showed that there is a recursive formula for the Jones polynomial, which is given by this expression where these coefficients C and I's are basically related by these recursive relations. So our idea is to first reformulate this result of Mishra and Staffeldt into a matrix form, and then use that matrix form, evaluate the Jones polynomial at t equal to minus 1, and prove the determinant formula. So after obtaining this formula, we came to know that this was already proved by OSPER, Stoimenau, Kim, Stees, and Thalmann, and Burton also in 2018. So this is a reformulation of the result of Mishra and Staffeldt into matrix notations, and the Jones polynomial is given by the product of these 3 matrices, Zt, which is written here, and m to the power n minus 1t, where m is this matrix, and C1 is this matrix, this column matrix, which is written here. So we want to evaluate this at t equal to minus 1. So this evaluation, first we get rid of this coefficient C2, which does not contribute anything in the determinant formula. So we consider submatrices of the matrices Zt, Mt, and C1t. So these are the matrices obtained after substituting t equal to minus 1, and we consider the matrices obtained by deleting third column, which corresponds to this, and so on in the other matrices also. And then we get that the Jones polynomial evaluated at minus 1 will be the product of these 3 integer valued matrices. So now we have to compute m tilde raised to power n minus 1, where m is this matrix. And this can be done usually by the diagonalization. So these are 4 are the eigenvalues of matrix M, and by diagonalizing and doing some calculation, we can get this formula. So let us move on. Okay, so if we move to the next complexity, let us consider the weaving knots of strand on 4 strands. So this formula was proved by Kim-Street and Thalmann by using the coloring matrix. So they wrote the coloring matrix, they observed some pattern in it, and then to consider its exponentiation and then take the first minor. So using that method, the authors proved that this is actually the determinant formula. And again, these determinants are a well-known sequence of integer, which is given by this A006235. And these are the values of the determinants, 1, 12, 75, and so on. Similarly, if we move to the next complexity, we consider weaving knots of 5 strands, then this is the formula that we obtain. So we will discuss this later. The method we use to prove this formula is based on the Burroughs result. So here we calculate the Alexander polynomial at t equal to -1 to obtain this formula. And the Burroughs result cannot be applied for with n even. Let me go back. So when this n is even, then this part vanishes. So we get in this equation 0 equal to 0. So this does not help in evaluating the determinant of that family. But with some computer calculation, we propose that the determinant formula for this weaving knots on 6 strands will be given by this nice expression, n by 3 times the determinant of 3 strand weaving knots and this quantity. So the determinant sequences for 5n is given by 129, 361, and so on. So this is not recorded in the online encyclopedia of integer sequences yet. Similarly, let us consider another family. Like this weaving knots are doubly infinite family. So let us consider the repetition index to be fixed and it is equal to 2. So if delta S is the silver ratio, which is 1 plus root 2, and PM is the mth Pell number, then this determinant is given by this expression, which is actually equal to the pth Pell number. So to prove this result, we observed that the Jones polynomial of these families, this family of weaving knots, satisfies certain nice recursive relation. So this can be obtained by using the Skene relation of the Jones polynomial. And as we can see, we want to evaluate this Jones polynomial at t equal to -1 and solve the recursive relations to prove this formula. But later we found that this was already known due to Dowdall et al. In 2010. They used the method of counting the spanning trees in the Tate graph of these families of weaving knots, and found that the determinant is given by the pth Pell number. And the sequence which corresponds to this determinant is well known. It is the sequence of Pell numbers. So we substitute t equal to -1 in this recursive formula and solve these recursive relations. So we get two linear recurrence relations. And by solving these relations, we get the desired formula. So this is just calculation. We get the formula in terms of the silver ratio, this one. So but as of now, we cannot give a general formula for the determinant of weaving knots. So let us move to this another interesting sequence, which is the sequence of twisted generalized hybrid weaving knots. So for these, we can give a formula which for all the members of this family. So the determinant is given by this expression. So it looks complicated, but this is precisely eigenvalues of some matrix which come from the Burrow matrix. So to prove this formula, we used the Burroughs result. And this has a very nice consequence. In a paper, Singh and Chabili conjectured that the determinant of hybrid weaving knots and hybrid weaving knots with a twist, which is called twisted hybrid weaving knot, are given in terms of Lucas numbers. So Lucas numbers is again another interesting family of integers, another interesting sequence of integers. So we can prove this conjecture by using this formula. So if we substitute m1 equal to m2 equal to m, then we get this formula and settle this conjecture. And for this m1 equal to m2 equal to m and L to be plus -1, we get this formula if we substitute it in the main formula. So this was conjectured in this paper of Singh and Chabili. Moreover, we can also obtain the determinant of torus knots by substituting M1 equal to Q and M2 equal to 1. So we get and take N to be equal to Q actually, and L to be 0. Then we get the determinant of torus knots from this formula. Moreover, for this family, if we substitute these parameters M1 equal to 1 and M2 equal to 5, then we get a formula in terms of Lucas numbers again. So why is this interesting? If we take L equal to 2 here, then in this family, the first member is the Parkhurst pair, which is denoted by this in the knot table, 10 of 161. So this is the Parkhurst knot, which is actually not a quasi-alternating knot, not an alternating knot also. So in this family, there are infinitely many non-alternating knots also, and infinitely many quasi-alternating knots as well. So for these knots also, we can get the determinant by using the main formula. So these knots are basically examples of twisted generalized hybrid weaving knots. So where these red color knots are basically non-alternating knots. So this is a small family of closed three braids, but it contains many interesting examples like weaving knots, torus knots, and these knots, and the like Parkhurst pair and so on. Okay. So the method to prove this formula is evaluate the Alexander polynomial at t equal to -1. So we use the Burrow representation and substitute t equal to -1 in this Burrow matrix of the generator sigma 1. And these are the matrices. So if we consider this braid and write the Burrow matrix of this beta, then substitute t equal to -1. Then by using the result of Burrow, substitute t equal to -1, we can evaluate the Alexander polynomial at -1 and consider its absolute value. That will give the determinant. So here the matrix appears, which is C power n, where C is this matrix given by A power m1 and B power -m2. So its exponentiation can be handled by finding its eigenvalues. So the eigenvalues of this matrix are precisely these two. And by diagonalization of this matrix, we obtain the desired formula for the determinants of twisted generalized hybrid weaving knots. So Kim, Stees, and Tarman in 2016, in their paper, they proved that the determinants of spiral knots with number of strands less than equal to 4 can be given by these formulas. So it includes weaving knots on 3 strands, this formula. Weaving knots on 4 strands is this formula. These are the torus knots, which is written in number 4 and 1. And this is also torus knot on 3 strands. And these family, which is mentioned in the 5th point, are almost torus knots. So their determinant is actually nice. It turns out to be k cube for this parameter 4, k, and epsilon is this. And all of these determinant sequences are well-known sequences of integers, which are given by these. So as we can see here, we have the alternating Lucas numbers -2. And these are the sequence of cubes of natural numbers and so on. Okay, so we want to extend this formula to n equal to 5. And this can be done again by evaluating Alexander polynomial at -1 and use the result of by using the result of Burrow. So by the same technique, we obtained that these determinants are given by these formulas. So this is the determinant of 5-strand torus knots, so which is already known, but can be given by this expression also. And these are spiral knots with on 5 strands with this parameter epsilon. This vector is given by 1, 1, 1, and -1. And there are 6 families of spiral knots on 5 strands, and all of them we can give a determinant formula. So this corresponds to the weaving knots on 5 strands, which we mentioned earlier. So these are some formulas which I wanted to present. And the 5-strand spiral knot determinants are actually given by these sequences of integers. So as we can see, we have computed it up to 10. So using those formulas, one can see that these are the determinants corresponding to those formulas. And we did not find any well-known sequence in these formulas, but there is an embedded sequence in the determinant of weaving knots. So if we look at the alternating numbers, this 1, 11, 95, and 781. So this is an embedded sequence in this sequence. So all of them are, these determinants are divisible by 29. And this is actually a known sequence in the online encyclopedia of integer sequences. We have checked up to 20 and so on. Like, so these are the formulas which I wanted to present. And here are the references. Thanks for your attention.
Thank you. Let us thank the speaker. Are there any questions or comments? Yeah, please.
Thank you for the very nice talk. Did you use the computer assist when you computing that determinant?
No, actually, we have proved these formulas. So we use computers to just to get what are the numbers actually. So just to input that formula in a computer and see what are these numbers.
And how you verify that the formulation resistance is correct?
Sir, we actually proved these formulas first. So these are proved, like which formula in particular you are asking?
No, I asked in general because it's very complicated. And how do you verify that is correct? So it's maybe very complicated result number. And how are you sure about that is correct?
So sir, correctness, like we have a proof for this formula based on the result of Burrow. So let me go back to the result of Burrow. So we actually used this result of Burrow to prove that formula. So we have a mathematical proof for that first.
Okay, thank you.
Its verification is like, so some of the papers we have already published. So those are well known, available on arXiv. You can look at the proof, how we are proving it. So for this spiral knots, it is not yet submitted. So, but other papers are already published. So, and they're available on the arXiv also. So you can look at the proof to verify or to check if there is any error in that or something.
I have also a question. As I remember, the determinant is related with some conjecture.
Yes, sir, one conjecture, yeah.
So did you check your notes? Are they hyperbolic? Did you check the conjecture of your notes?
Sir, this conjecture we proved, which is a conjecture of Singh and Jabili. So what is your question? Like, let me go to that slide first.
What hyperbolicity of your notes? All of them hyperbolic or not?
Hyperbolic or not? So weaving knots are hyperbolic, but we do not know about this entire family of twisted generalized hybrid weaving knots.
Other you don't know, yes?
Yeah.
Oh, okay, thank you.
So because there is a twist factor, so some of the knots may not be hyperbolic in this case. So that we have to check which are and which are not.
Thank you. Let us thank the speaker again.